Good morning, students. I just wanted to give a quick overview of the study guide and what you guys should be able to know to prepare for this exam. There's Study Unit 1, Introduction to Digital Concepts. You need to know what are digital and analog signals and define and speak about a little bit about themselves. And also what are binary levels, low, high, what constitutes the unacceptable case. You also need to know what the pulse width is, what's a period, and also from that you need to be able to calculate the duty cycle. Then moving on to number systems. Expect you to know all the number systems, binary, converting binary to decimal. Expect you to do binary arithmetic, binary addition, and binary subtraction. Also multiplication, and finally division as well. I need to understand ones and twos complement, and converting ones and twos complement to decimal. Need you to understand signed binary numbers, and understand that this signed binary, the first bit is only the sign bit. So once again, signed binary numbers, we have three types: signed binary, the magnitude, where the first bit only indicates a plus or minus. You have ones and twos complement. Then also expect you to do octal numbers and convert from octal numbers to binary, and from binary to octal. And also hexadecimal, same thing. You need to convert hexadecimal to binary and back again from hexadecimal to binary. So very important, converting binary to hexadecimal and also hexadecimal back to binary. And also same for octal, converting octal to binary and back again. You also need to understand what BCD code is, and it's basically just using 4 bits and 4 bits to represent decimal or even hexadecimal or decimal numbers. You need to understand what gray code is, also alphanumeric codes, understand error detection codes, and even parity and odd parity and how they work. And yeah, modulo 2 operation CRC process I don't think is so, but I think parity is a bit more important. So need logic gates. Now for logic gates, you need to know the truth tables for the NOT gate, AND gate, OR gate, the NAND gate, the NOR gate, and the exclusive OR gate. Now an easy way of doing it, I believe, is, now NOT gate is pretty easy. Memorize the AND gate, because it's also pretty easy. It's only 1 when both inputs are 1. Memorize the OR gate, which is it's only 0 when both inputs are 0. And the rest is, if you have a 1, it's definitely a 1. Because from the OR gate and the AND gate, you just invert it to get the NAND gate, because this is the NAND gate, just the opposite of the AND gate. And the same with the NOR gate. Is the opposite of the OR gate. Then you have to just remember the exclusive OR gate, which is like an OR gate, but the only difference is if all these if the inputs are the same, then it's 0. Okay. And also exclusive NOR gate, if you know the NOR gate. You also need to know 3 input gates, because these are exclusively for AND gates, 2 input gates. Now, if you have a third input, the truth table for the AND gate doesn't really change. It still remains the same. If all the inputs are 1, then you might have 1. And the same thing for an OR gate. If all the inputs are 0, then it's 0. If you have at least one input 1 for an OR gate, it's a 1. Okay, so just bear in mind of 3 input and OR gates. Also, I need you to know the design of an IC, how the pin numbering works. I think there's a little bit something, but you have this notch here, or a dot, indicating where the first pin is. And please be aware, so you look at the notch, left side you have 1, 2, 3, 4, 5, 6, 7. You start on the other side, 8, 9, 10, 11, 12, 13, 14. Nomenclature of IC is just good to know. And here we have the numbering. So firstly, on an IC, you look for the notch or the dot, and directly left of it, you start counting at 1, 2, 3, 4, 6, 7, 8. Now, always in exams and tests and assignments, a question on IC numbering will pop up eventually. Okay. So here we have Boolean algebra and logic simplification. Now this is mostly about the rules of Boolean algebra. Please, you have to know these rules, these 12 rules. They are given as an annexure in the exam, but it's better if you know what they mean, because it makes everything a lot easier. And it's quite simple. A or 0 is always A, because that 0 doesn't mean a lot in an OR operator. A or 1 is 1, because if you OR anything with 1, it's 1. A and 0 is 0, because if you AND anything with 0, it's 0. And A and 1 is A. A and A is always A. A or not A is 1. A and A is A. And A and not A is 0. If you have a double complement, it cancels out. And these 10, 11, and 12 are also very example. So have a look at the rules and how you apply them with all these. You don't really need to know the definition, or not the definition, or how they're derived. Just know all the rules and how to use them. And also how to use De Morgan's rule, i.e. breaking the line, change the sign. Also be aware of standard forms. And it's very important to count the amount of variables, different variables. So A, B, C, and D. So we have to add in the D. But other examples, we have A, B, and C. So there's no D. So if there's no D, oh, here we have a D. But sometimes there isn't a D, so you don't need to add a D to get into product of some standard form or unstandard form. Constructing a truth table from a logic circuit. Have a look at, I usually number the outputs, and then write down the numbers and then the output of that circuit, making it a lot easier for me to construct an expression or truth table from a circuit. Column maps are very important. We use them all the time. Also from truth tables, know if it's a 0, it's POS, and 1s are SOP, standard forms, but we'll get to that a little bit later on. You must know how to set up and draw column maps. So 0, 0, 0, 1, 1, 1, and 1, 0, and 0, 1 if you have only 3. And this is a 4 variable one with 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 1, 1, and 1, 0. And please be aware that when you're doing column maps, you can group must contain 1, 2, 4, 8, or 6. That's all powers of 2. Each cell in the group must be adjacent to the one same group. Always include the largest possible number of ones in a group. And every single one must be included in these groups. And you have the overlapping sides. So that group there overlapping with that one. And please be also aware that when you group the column map, how you decide which falls away. So 0 A goes from 0 to 0 in this group here, so it stays as a not because it's 0. B goes from 0 to 1, so it falls away. And C just stays 1, so it stays C. Please be aware and follow the examples on how you simplify using a corner map. This is code converters. Just be aware that they exist and how you can possibly use them. And also go through the design question, where I give you and I've answered this question before. There's usually a couple of steps you need to follow. First, read the question. Then write down what the amount of variables we have. In this case, we have 3 variables for each wheel. And then what the outputs are. So we have green and red LED. And then write down what happens, the conditions, why, when they're low, when they're high. Then once you have those information, then you can do a truth table. From the truth table, you can write down the SOP conditions or POS, whatever you want. You can fill in the corner map, then you can minimize, and then you write your circuit diagram if we need you to do that. Now we get on to combinational logic analysis. Now we start off with the universality of NAND gates. So you can use a NAND gate to represent any other gate you want. Here is probably the most important one. If we want to implement a NAND gate, as a NOT gate, you just wire the NAND gate to itself, and then the input is inverted. You can also have it as an AND gate. So you basically just have a NAND gate output there, and then you complement it, and then you have an AND gate, an OR gate, and a NOR gate. But for me, the most important one is this one. You can do the same with OR gates. It basically works in the same way. If you wire it to itself, then it inverts. But very importantly, if I ask you to convert an expression to be able to use by NAND gates, what we do is you add in those double complements. Then you break the line, change the sign, get rid of all the signs you don't need, and then implement just with NAND gates. It's very important to read the question and do what I ask you to do. Usually I would get tips. I will ask you convert it with NAND gates, and then from NAND gates implement only with NAND gates. And if I ask only with NAND gates, please only use NAND gates. And this is just examples of NAND gate implementations. Now chapter 6, functions of combinational logic. We start with adders, a half adder and a full adder. Now I do expect you to know the truth table for a half adder and the truth table for a full adder. Now it's a half adder is simplish because you have 2 inputs, 2 outputs, and it's just you're adding these 0 and a 0 is the sum is 0. 0 and 1, sum is 1, carry 0. 1 and a 0, the sum is 1, carry 0, and a 1 and a 1, the sum is 0, but the carry is 1 because the answer is 1, 0. And same thing with full adder, you just have a carry in. Now I do expect you to know the difference between a half adder and a full adder. I need you to can explain that through the truth tables and the truth tables here, and also know what the logic diagram is for a half adder and a full adder. And here we have the design of a full adder, which you also need to be aware of. Here we have parallel adders, where you cascade parallel adders in order to count bigger numbers. Just here is comparators. So I need you to know what a comparator is, equality and inequality, and how they work. So here we have an exclusive NOR gate for equality comparator, and for here's a higher order equality exclusive OR gates, and also inequality. I need you to know how inequality works, why we need equality and inequality comparators. Here's decoders. I need you to know what a decoder is, and I also need you to know what's the difference between a decoder and an encoder. And I need you to look at decoders and encoders, tell me what they are, what's a decoder, what's an encoder, and in what applications they're used, because that also highlights the difference between the two. Now we have multiplexers. And I also need you to know how a multiplexer works. I might give you a multiplexer diagram like this, give data inputs, and then ask if the selection outputs on this, let's say 0, 0, the output is D0. If the switches are at 0, 1, the output is D1, 1, 0 is D2, 1, 1, D3. So basically with this data select switches, you select which data line you want, and you make up a binary number between 0 and 3, and then that selects the data line. So you will need to know, if I have this on the data select inputs, what output I would take and what would be displayed on the output. I also would need you to know what a demultiplexer is and what is the difference between the two. Now it's quite simple if you don't know. So a multiplexer, it takes a lot of data lines and puts it onto one output. So a lot of inputs onto one, mainly to one. And demultiplexers, you have one data output input and lots of data output lines. So multiplexers, many to one, and demultiplexers, one to many. Just examples of demultiplexers. And also I'll do a special video on a 7-segment display, which is also very important, and things you need to know about 7-segment displays, which I don't think everybody does. And now the last section is the AND or invert ICs for implementing SOP expressions. It's also very important to know what these representations are. And here we have our little ICs pin layers once again, just to remind you what these are. And this basically just talks about ICs and their implementation and an OR. And with this, I also need you to know SOP conversions, going from an SOP to POS. And I've already done a video on that as well, just have a look at that. And then we just go on to the activities and the data sheets at the end. So please have a look at the videos, have a look at what I've said, and go through the study guide and study everything that you need to know. I will do a video on 7-segment displays, which I will upload hopefully this week before the exam, so that we are all